And we're back. Now we're back. I'm waiting as fast as I can. I'm doing my best. So, welcome back to Lecture 6. No time has passed. Oh wait, how do I normally do that one? There we go. 6.5. Oh my god. So the way that I had this series worked out in my head was that it was going to be 8 lectures, or 8 streams, 8 of a thing. And it took too long last time, so we've broken it up. But this is now going to be all about elastic collisions. So last week's stream we looked at elasticity just inherent in strings, springs, and the like, or modelling things as strings or springs. And that was where we had things like Hooke's law appear. Okay, we had... So the force or the tension within a string or a spring is proportional to some modulus of elasticity multiplied by the extension length, so the difference added on, and then divided by its natural length. And what that tells you is there's this proportional relationship with how much we deform a body with how much force it requires or it holds. So if you think with a spring, the further away it is from its sort of rest state, the more force required to hold it in that position or to stretch it out. And there's also a proportionality between the modulus. So the larger, for like really, really big, very stiff, not really elastic. So things like steel beams are going to have really high modulus of elasticity because they're really not elastic. That thing does not want to bend. Whereas a small lambda is very elastic. Okay, like as your normal springs, strings, etc., etc., they're all going to be really easy to move. So it gives us this nice proportionality. And then we also looked at elastic potential energy. Which was EPE is equals to lambda x squared over 2L, which the astute notice is the integral of the right-hand side of that Hooke's law, so the force required, and now you have the energy stored. And that is precisely what gets converted to kinetic energy when, for example, a compressed spring releases. So we looked at those two concepts. So this is our sort of like previously, or on last season or last episode. But today we're going to do collisions. So 6.5.1 is going to be 1D collisions. And then, unsurprisingly, we're going to go on to 2D collisions. We're probably not going to do 3D. That is kind of out of scope. And arguably unnecessary. Who knows? I graded a spring pendulum lab report today and had to fail too many students for not being able to add spring constants in parallel connection. Oh. Addition is hard for uni students. 3D collision is 2D with extra steps. Who boy do I have news about 2D collisions. That is way too hot. Let's put that down. Okay. So by 1D collisions, we mean things which are moving and impact along the same line. So, for example, if I were to throw a ball at a wall, which is going to be the iconic example that we use in both 1 and 2D, the direction of motion, it has to be perpendicular to that wall for it to be a 1D collision, because it's going to hit, collide, and then bounce back in the same direction. Everything is, picture it all stuck along a string, not an elastic string, an invisible string. Everything is motion, all impact, all collisions, all work along that one string. They work along that one line, even. In 2D, then, things can hit at angles and bounce back at angles, and we get all sorts of complicated stuff happening. New physics just dropped. 2D is just like 1D with more steps. That way they kept Starman up all night. Neo? Although, it should be morning for Starman. We might see the end of the, we might see the end of a Starman. Who knows? Okay, so in order for us to start doing collisions, we have a new rule to introduce, okay? And this is something that I used a lot in my PhD, but Starman just gets to work incredibly early to catch a stream and meme on us. I mean, yeah, pretty much. This is a motivation for getting up and doing things. Forgot what I was saying. I would never. Yeah, I used this law a load in my PhD because I was looking at things bouncing. Bouncing is an impact. Things are going to bounce back. This elastic collisions is my PhD, basically. Make the things more complicated and you get my PhD. So our law is called Newton's law of restitution. Yeah. This relates the speed of a particle pre and post impact with its material properties, i.e. how elastic it is, how bouncy it is. Right, now, I am not a material scientist, so this is sort of where we draw the line on that one. But the law in the equation is E is speed of separation over, thank you for the follow, welcome in, over speed of approach. Okay, so it is a balance law, it's a fraction of an amount. So you have two objects, or one object hitting another object if one is stationary, but two things involved in a collision. You take their speeds as they approach the collision, and then their speeds after the collision. And it's essentially, it's a fraction of that initial had they never collided amount. And what that tells us is E is between 0 and 1, where E equals 0 is a completely inelastic collision. Okay, so for example, if I throw a dart at a dartboard, I was like trying to think of an example that made sense. If I throw a dart at a dartboard, the speed of approach is some amount depending on how fast I can throw, but the speed of separation is 0. It doesn't separate. The two things stick together, and we say that that is a completely inelastic collision, or a perfectly inelastic collision, because there is no bounce back. There is no ricochet. It's stuck. Now, physically, there is like probably some, like a small amount, but for all intents and purposes, that is 0. Where's my page gone? The opposite end then, E equals 1 is perfectly elastic. Okay, so here the speed of separation and the speed of approach is exactly the same. That could be two things that don't end up colliding. They have no effect on each other whatsoever. Or probably what's happening in a perfectly elastic case is there is no loss of energy. There's no elasticity, there's no deformation. It perfectly bounces back and the two things don't lose any energy by contacting. If I tackle hug you and not let go, that's completely inelastic. It is, but ask consent first. But yeah. Most rugby scrums, inelastic. Yeah, so a perfectly elastic collision, there is no energy loss, right? The speed is the same on both sides, and as we know, if the speed changes, the kinetic energy changes, so some energy is lost in some way, shape, or form. Where no energy is lost. And now, obviously, both of those examples are very, very specific, so typically E doesn't really tend to touch those two end cases. They're sort of the extreme values. So what does that look like in maths terms? Well, we have if we have our normal way of doing collisions from when we did impacts and impulse and momentum, we had our sort of two objects going towards each other, where this would be UA and UB, where this object is A and this object is B. And then I would have post, and I would have, say, for example, them moving away from each other. With VA and VB. Then I would have E is VB minus VA over UA minus UB. Okay. And note here that the sign changes are typically corresponding to the positive and negative directions, right? So here in this equation, that way is positive, right? So you have VB being positive, VA being negative, because it's going in the negative direction. And then UA is going in the positive direction towards my head, and UB is going away from my head that way, towards the negative. So sum of positive speeds, sum of negative speeds. If they were both going in the same direction to start, but the one behind was going faster, you would sum the two of them. Yeah, that's what you would do. So there. Okay. If a particle were to collide with a wall or unmovable object, the same rule would apply. Where U all equals V all equals 0. Doesn't move. Okay, so if we were going to do this example where instead of two particles they were colliding, it was a one particle and a wall, you would just take the wall's speed at both times to be 0, but the rules still apply. For all intents and purposes, when perfectly spherical particles, ooh, can I do this? This is the question. There we go. Ah, and then I can do this. Okay. So when a ball collides with a wall, it only touches at exactly one point. Okay, it touches at that tangent. So only one teeny tiny part of the wall touches, okay? So there's only one small dot on the wall that gets in contact with the ball, the particle. When it's two particles, the same thing happens. They only touch at one teeny tiny amount. So for all intents and purposes, whether it's a ball or a wall or a shape or whatever, typically when we're looking at particle collisions, it's all basically the same thing. So you can model the particles coming together as one particle hitting a wall, if that's easier for whatever reason. Obviously, if it's going to move, it's better to like visualize it with spheres because we think of them as moving more easily than giant walls. But that is going to come in useful later when we start doing 2D stuff. So, let's do a question. Visualize them as point spheres in a vacuum. Yes, exactly. So two particles P and Q. I'm so sorry for the typing noise. Just mute me in a minute if that's better. Two particles P and Q are moving in opposite directions along the same straight line on a smooth horizontal surface. When they collide directly. The mass of P is 3m, and mass of Q is 4m. Immediately before the collision, the speed of P is 2u, and the speed of Q is u. Ah, you can't see that one. The coefficient of restitution, which I should have specified, is this E. So where Newton's law of restitution defines the coefficient of restitution. Okay. I still have the shape recognizer on, that's why that was doing that. Okay, so part A of this problem. How on earth do you spell immediately? Who knows? Okay, so two particles P and Q moving in opposite directions along the same straight line on a smooth horizontal surface when they collide directly. A nice little trick that questions will use when they don't give you diagrams for this sort of thing is secret trick question. I told you they were moving in opposite directions and I actually implied they were moving away from each other. However, I've said when they collide directly, implying they are moving towards each other. Mass of P is 3m and the mass of Q is 4m. Immediately before the collision, speed of P is 2u and the speed of Q is u. Coefficient of restitution between P and Q is e. Find the speed of Q immediately after impact. So if we were going to do this, or we are going to do this, first thing I always do, immediately, I thought it looked weird. There we go. is draw it out. So I have P. I'm going to pretend they're moving along the same straight line. And I have Q. And I know that P is moving with 2u, and the speed of Q is u. So this is actually minus u, because I'm going to set positive, as always, to the right. Okay. I'm also going to draw in force downwards. Now I don't know. Oh, they are on a smooth horizontal surface. There we go. But this mass is 3 mg, and this is 4 mg. Okay. I then have the post-collision labeling them, and I want to find this one. Okay. And this is going to be some value v. So let's label this actually VP and VQ. So we're told to find VQ. So there are two things that we can do here. There's the first rule, so this is why I kind of wanted to keep things going from previous. So we're going to need to use, let's do the answers in orange actually. Let's mix it up. We need, so there are two unknowns. So we need two equations. If we knew what the speed of P was already, we would be able, see, this is your first way that I move on a straight line, queer lines only, mood. However, this is what we have. If we knew what the speed of P was after collision, we would only need one equation. However, we always need the same number of equations as unknowns. So one that I'm going to use is my coefficient of restitution. So that's my VQ minus VP over U minus 2U minus U. And apparently it is minus U. There we go. And then the other one I'm going to use is conservation of momentum. Okay, so because we've been given the masses, we are able to use the momentum of the particle. So momentum is conserved in both cases. So it's momentum before, equals to momentum afterwards. So if this is something that looks completely new to you, sorry, my brain is just completely short-circuited. If this is something that looks completely new to you, there should be episode or lecture 4, I think, was momentum and impulse. It might even be 5, but we did do momentum and impulse before. But this will give us, so it's the momentum is mass times velocity. So the first one is 3m2u minus 4mu. So that's the mass of P times the velocity of P minus, well, it would be plus, but we have that minus u. 4m is the mass of Q. U is the velocity of Q, equals to 3m Vp add 4m VQ. So we don't know which one of those is negative. We're assuming that they bounce back, but we will make do. Okay, so solving these outwards, we get E is VQ plus VP over 2u minus u is 3u. So 3EU is VQ VP. Okay, so I'm actually going to set this as 3EU minus VQ equals VP, so that I can then plug this into the other equation. Solving here, we end up with, we can cancel through all the m's, which is going to make our life easier. Okay, so that gets rid of those. So then we end up with 6u minus 4u is 3vp plus 4vq. 6 minus 4, so we get 2u is 3 lots of, and then I'm going to plug that equation in over here. 3eu minus vq plus 4vq. Okay. Solving this then, you get 2u is 9eu minus 3vq plus 4vq. I will stop saying vq any minute now. Simplifying, we get 2u minus 9eu is vq. Now, for some reason I should have a minus 7. Why should I have a minus 7? Hello there. Right, what have I done? 3m minus 4mu. Ah, okay, they bounce back, so that should be negative. That should be negative. That should be negative. There we go. Okay, let's pretend I didn't do any of that and do it again. Just to be clear. Okay. So momentum before, and this is why we should have the diagrams up, because that will be actually helpful. Okay, so the momentum before, we have 3m 2u minus 4mu equals 2. Okay, and then we have the positive VQ, so 4m VQ minus 3m VP. Yes, we can cancel through all of the m's. So what we end up with is 6u minus 4u, getting ahead of myself. 6u minus 4u is equals to 4vq minus 3vp. Then I'm going to simplify the left-hand side and then substitute in. So I get 2u is 4vq minus 3 lots of 3eu minus vq. That gives me 2u is 4vq minus 9eu plus 3vq. Getting there. Take that over to the other side. 2u plus 9eu is 7vq. And finally, that gets us the vq, so the speed of q after collision is, what is it? 2 plus 9e u over 7. Ta-da! Phew! Take one of these signs, you can take it when you need it. Ha! Yeah, much needed. What is E here? E is the coefficient restitution. So just to recap, the question was you have two particles moving towards each other. You get given the masses and the speed and the coefficient of restitution, which is sort of measure of how much they bounce back, all sort of symbolically. So because there were two unknowns, we needed two equations, so we took conservation of momentum and coefficient of restitution. So that was part A. Part B of that question then is after the collision with P, Q collides with a fixed vertical wall and rebounds. How much space do I have to write there? I'll type it out and then read it out. That was only part A. I know, there's more. Scandalous. Okay, so no pressure. After the collision with P, Q then collides with a fixed vertical wall and rebounds. The wall is perpendicular to motion. So that's what I was saying about things only moving in 1D. It has to be perpendicular so that it can touch at the tangent that's in line with the centre of mass to get it to bounce. Whew. Coefficient restitution between the Q and the wall is now 0.5. We have another value. This is good. Find the complete range of possible values for E, for which there is a second collision between P and Q. So, things to know. Point. If there's a second collision, it implies that speed of Q was greater than speed of P. Okay? And that's basically because when you think about it, you have sort of this happening in phase 1. Then this presumably is going to bounce back, and this is going to go over here. And now there's a wall. I think all lecture should be done to this song, by the way. And now this one's going to be sort of over here. So in order for this to catch up, it has to be faster so it can slow down. If you have trouble visualizing a wall, just think of an infinitely large sphere. Yeah, sure. So this is P, this is Q, this is wall. Okay, so we know that this was 2u and this was u, and we know that this was u over 7, 2 plus 9e. We called this VP, and then this will also be VP. And then we need this value, I'll call it WQ, to be faster than VP. Okay, so first thing we need to do, find VP, find WQ, compare for E. Okay, so these are the steps we're going to do. Why a sphere, why not a plane? I mean, if you have trouble visualizing a large wall, I imagine a large plane is going to be the same level of difficulty. But who knows? Ta-da! The large sphere isn't. I mean, I'm not one to question. It's a suggestion. Okay, so this is what we need to do. No pressure. And I'm going to label these collisions. So this was collision 1, this is collision 2, and then this is the maybe collision 3. So, for collision 2, we have the E is, so what is it? The out speeds. Let's copy. The background just moved. Oh my god. Okay. Also, the speed here is like speed wall is 0. Like always 0. So essentially it's only really Q's speed out. So this is WQ over the speed in, which was that value we worked out before, which was U over 7, 2 plus 9e. Blech. Okay. And I'm going to call that E2, and then this is the E1. This is that value E that happened. So we got told that E2 was 0.5. The coefficient of restitution between the ball and the particle Q is 0.5. So it's perfectly halfway between an elastic and an inelastic collision. So it's like an average collision, basically. So we have 0.5 is equals to WQ over this nonsense, U over 7, 2 plus 9e. So multiplying or swapping those all around, we get that WQ is equals to U over 14, 2 plus 9e. Okay, so I just took the U over 7, 2 plus 9e over to the other side, flipped them, times in by 0.5 is dividing by 2, 7 times 2, 14. So that gives us this value. But we still needed to find VP, so I did that in the wrong order. Finding VP, we're going to use part A. So you remember how all the way up here, we had this equation. VP was 3EU minus VQ. So VP is 3EU minus U over 7, 2 plus 9E. Okay, getting somewhere. The EU is going to affect that latter half of the term. So we can take the U over 7 out the front. Actually, let's just expand it because that's easier for everyone's brain to see where I make a mistake. Minus 2U over 7 minus 9EU over 7. So we end up with U over 7. The 3 goes to 21. 21 minus 9 is, don't tell me, 12. Ta-da! Thought we left the EU. Yeah, don't remind us. Okay, so we have our value of VP and we have our value of WQ. So, 3. Thank you for the follow. Welcome, welcome. The second collision happens for WQ greater than VP. Love math and UK. We love some of those things here. So we have U over 14, 2 plus 9E, which is our WQ, greater than VP, which was U over 7, 12E minus 2. Okay, so let's cancel down a load of stuff first, so we can get rid of the U's nice and easy. We can get rid of that 7, and we get rid of that, and that becomes a 2. So we can multiply it by the 2. So we get 2 plus 9E greater than, times everything by 2, we get 24E minus 4. Get rid of U because U is greater than 0. Yes. Yeah. If U was 0, then none of these collisions were going to happen. I think is what happens. If U was 0, everything breaks. Basically. We're assuming U non-zero. Yeah. Stop it. You know what I mean. Okay, so we get 2 plus 4 greater than 24 minus 9. E, so we end up with 6 greater than 24 minus 9 is 15E. So 6 over 15 greater than E. So a second collision . So when that is greater than the E, so 0 less than or equal to E less than or equal to 6 over 15. 6 over 15 can definitely be simplified. So is it 2 over 5? Divide it all by 3. And we put the lower bound back in, even though it's implied because E is confined between 0 and 1. But just to be thorough. And that makes sense, right? Because 1, if we go up to what the values of E mean, all the way up here somewhere. Smaller values of E. More energy was lost, whereas the... Oh, I don't know why that makes sense physically. Let's leave it for a physicist. I suppose if it was perfectly elastic, it just wouldn't have... We go back to the whole U is 0 thing again, and they're just going together. I think it's because a lot of the energy was lost in P... Oh, yes, because Q's the bigger object. So P loses a lot of energy. Momentum always conserved, total kinetic energy may be lost. Yes, because some of it goes into elastic. I was summoned, but I was not paying attention. Womp womp. Now we'll never know. Now we will never ever know. It's very sad. Right, we're going to take a really short break for a second just so I can go get some more water, and then we will be back and we're going to do 2D collisions. So don't go anywhere except maybe like for a little wander. For a little wander. Can E be negative? Technically no, in the confines of this system. However, if it were, then you would have something that's like kind of gone through something else. Picture like a stationary target and a bullet. I don't know, the speed's still positive. Don't know. Have a think about it. Come back after the break. See you soon. Bye-bye. Hello. We back. Surprise. Yeah, so essentially, no it can't. However, in my PhD, did I mention that my PhD was on bouncing droplets? So impacts and collisions and all of that good stuff. It depends where and how you measure coefficient of restitution. So for a droplet rebounding, there were 3 key metrics that we measured, basically, to say how bouncy a droplet was. So I was looking at droplets of water, like millimetric, like tiny, tiny droplets of water bouncing on baths. Actually, the other way. So we had negative coefficients of restitution because in order to measure speed in, speed out, right? Speed is constantly changing when something's actually like falling due to gravity, or sort of bouncing. When it's really springy, remember what we said, right? The tension is dependent on how far away it is from its rest state. So we're going to, down the line in 2 lectures time, look at something called simple harmonic motion. But you get this like spring habit where like it's faster on the edges, or it's slower on the edges and it's faster in the middle. So when you had something bounce, you needed to sort of pick a height over the bath to count speed. So speed in, speed out only works when you measure them at the same like height above surface, above the water. Okay, like I'm going to measure how fast it is moving past this line in, and I'm going to measure how fast it is moving past this line out. And what was happening with some droplets is they were bouncing, they were going past this line, but then they never got back up to the line. So think of like, where's my random aside colour? PhD chat. What was happening was you have this sort of, this baseline here, where we're like, right, we're going to measure speed on this point. And normally it would be like this, and then it would rebound and it would come back out, and it would be all fine because you'd measure this point here and this point here. But when it went in and then never hit back, we can't measure an out speed. But what we can measure is the energy. So we can't measure a speed, it never crosses the line, but we can measure an energy loss. And what we end up with is this gap here. And if you remember from Hooke's law when we were looking at it, there was a relationship between Hooke's law and the elastic potential energy. There's a similar sort of thing going on here. So we looked at the energy difference in the droplet. And basically what that gave us was a measure that was sort of like E squared. It was if you look at the kinetic energies, right? You have if E is out over in, out squared over in squared, but out squared is half mv squared over half mv squared. You can cancel the m's, you can cancel the halves, you get v squared over v squared. Sorry. So we had this value where the out was negative, or the in was negative. But essentially, things went really squiffy and we ended up with negative coefficient of restitution. It is not actually coefficient of restitution, but for all intents and purposes, it is coefficient of restitution. But we managed to get E squared equals something negative. Because we didn't use the velocities, we used the energies, and there was an energy loss from the system into some secret other thing. Speedy thing goes in, speedy thing comes out. Professor Gladys. I tell you what we should do. Me and Thomas should really finish that playthrough of that thing that we did ages ago, Portal, that we started absolutely a decade ago. That would be fun. Okay. So, kind of covered brief overview of 1D collisions. Now we're going to do 6.5.2, 2D collisions, which I'm sure are a surprise to absolutely no one. So when objects collide not along a straight line, we call the impact oblique. And oblique impacts for droplets was something that I always wanted to get to in my PhD because it just makes things so much more complicated. And it's really fun. But visually, what I want you to think about here is sort of this sort of behavior going on, okay? Where now we have these two angles, alpha and beta, and there's no guarantee that those two angles are going to be the same, but it's a hitting not in the direction of motion, okay? It's not fully perpendicular. And surprise to no one, this is going to need trig. Basically, if you want to exist in the world, you probably need to know Pythagoras' theorem, is the annoying thing of if you want to describe anything, it's probably Pythag. Also, yes, in the break I saw there was some chat. I have added the YouTube link down in the About section now. Hopefully that's there. These will get uploaded about on a week's delay. Plus or minus me being functional, basically. So, when a body impacts a smooth surface. The impulse still perpendicular to the surface at the point of impact. So again, we did momentum and impulse way back when, but when two things collide, there is like a sudden impulse that happens. And what this is saying is that this happens at 90 degrees to that surface. So even though the collision happens at an angle alpha, the impulse is going to happen 90 degrees. And then what happens is we can resolve things in parallel and perpendicular to the impulse. So if I do another drawing and make it even bigger this time, so again, we have our alpha and beta just to label the angles. Again, we're going to say that the starting speed is u and the final speed is v. And we're going to have that the impulse moves okay. So resolving things horizontally. We have two equations. One of them in line with the impulse, which gives us our coefficient restitution behavior, and one that is horizontal. So if we think we're coming in at an angle, we have this horizontal speed of motion of the ball is breaking that u down into these angles. We have u cos alpha. And then again, when it's moving upwards, so this is coming from the fact that here we have v, we have beta, no, how do we do this again? It's like that. So if that's v and that's beta, then the one adjacent to it is v cos beta, and the one not adjacent to it is v sine beta. And the same over here, where we have u z angles puts that as alpha, so that's u cos alpha, u sine alpha. Okay, recap on trig for that one. But yeah, so the horizontal motion is our cos values, and then that's v cos beta. And then vertically, so we have the speed down and the speed up, but we also have this coefficient of restitution. So we can do our coefficient of restitution, measures how bouncy upwards it is. Doesn't really impact the horizontal because there's no impulse in that direction. So this gives us E is the outward speed, so V sine beta over U sine beta, or V sine beta is equals to E U cos. Sine. The sines go with sines and the causes go with causes in this case. If I get it wrong, shout at me. What we can do, however, is we can combine these equations to give. So if we divide the vertical equation from the horizontal equation, we can divide one side by the other. So we get V sine beta over V cos beta. V sine beta is E U sine beta over U cos beta. V divided by V, cancel those, U divided by U. And what we get is tan of beta is E, and I have already written it wrong. There we go. Alpha, alpha, tan of alpha. So we get this one equation for the angles and or one equation for the coefficient of restitution and the angles. So that's nice. Bonus stream on the history of the Pythagorean theorem. We can go full conspiracy theory on the Pythag stuff. I actually have one of my talks that I do, which I am hireable for all maths communication based gigs to do, is all about how Pythagoras basically nearly broke music from his like necessity for things to be perfect, which is quite a fun talk. So. Okay, so this gives us an equation for the angles and E, and we also have that since E is between 0 and 1, right, it's going to be a fractional-esque amount. We have that tan beta is going to be less than or equal to tan alpha, and this works because it's tan values, beta is less than or equal to alpha. I.e., angle of rebound is always going to be less than or equal to angle of approach. Okay. So this is just super useful to know that sort of fact checking ourselves, we're never going to be able to bounce so much that it jumps higher than it started with, essentially. It's never going to come in at a sharper angle than the one it came in with. For a perfectly elastic collision, it's going to bounce back at the same angle, but it's going to be the same or less. And that makes sense intuitively because there's no extra energy being added into this. If it was a trampoline or bouncing on, say, a liquid bath, maybe it would get some energy from another source. But for these style of collisions, no. So, final comment. Successive impacts. So this is something where, say you have walls at an angle to each other, which, spoiler alert, we will have at some point, and you bounce in, and you bounce across, and then you bounce out, and you can keep going forever. If you've ever watched those TikTok videos where things are just bouncing in like a hexagon, is cool stuff. But the same rule always applies, so eventually it's going to run out of energy, because if that's angle 1, angle 2, angle 3, and angle 4, 1, 2, 3, 4, then 2 is going to be less than or equal to 1, and 4 is going to be less than or equal to 3. Now, the angle between 2 and 3 is dependent on how those walls are next to each other, but you're going to potentially lose some angle between them. But successive impacts can be computed separately by resetting the frame of reference, basically. So okay, so by that I mean that for this collision 1 here, we have our frame of reference horizontal and perpendicular to this wall, and then as soon as the particle leaves that wall and that collision, we reset our frame of reference to now be aligned with the new wall. So we change to kind of shift our head so that we're looking perpendicular and parallel to the new wall. So that's quite nice. The other thing would be a 2-particle collision. So this is where it starts getting really useful if you want to understand how like snooker works. So you have 2 balls that are gonna... Is it gonna let me do a fancy line? No. So these things have... There we go. So you have 2 particles colliding. You might think it's getting complicated, but remember what I said before about they only touch at one point? Well, now we still have, they touch at the tangent, which means that the impact, the impulse moves perpendicular to that, and it's going to move through their center of motion. So regardless of what angle they're coming in at, because they touch at a single point. So, where can I write this? There. Because the 2 touch at one point, they have a common tangent, it's called. So you think when a ball hits a wall, the wall makes the tangent with the ball. Now, from the perspective of one of those balls, the other ball is the wall. So they have a common tangent to which the impulse is so the impulse is perpendicular to that common tangent, and it also works through the 2 centers. So that's sort of point 1, and then point 2 with this is note the impulse will be the same on both particles. So just like in 1D, just like with normal collisions, it's the same impulse. It's the every force is the equal and opposite. The impulse works in both directions, so it's the same impulse. So if you have, let's do some diagrammy type stuff. So you have 2 spheres that are gonna collide, say at some angle, and this is A, and this is B, and this is UA, and this is UB. And sorry, I hate writing in capitals. I don't know why I keep doing this to myself. So this is A, this is B, this is UA, and this is UB. Then I'm gonna give myself a little bit more room. Then when they collide, okay, trying to draw circles is, there we go. When they collide then, they touch at a common tangent. That works perpendicular to their center lines of motion. So, good thing to keep in mind here is sort of their center of motion. Like, yes, they touch at this angle at the tangent. but they have their initial speed coming in sort of corresponds to this there, and then they have their speed coming out, so they're going to bounce back at some angle. So now the angles that they compute, so you have your UA and your VA and your UB and your VB. So you have this angle here is alpha, and that angle there is the beta for the A values, so A alpha, alpha A, beta A, but I really don't want to do that. Alpha B, beta B, okay? There we go. There's too many A's and B's is what I'm learning quickly. So now the angles are working in this line, and you have, again, the impulse works perpendicular to that common tangent. So it says, for all intents and purposes, UA is like, it's like looking at a vertical wall. So it could, carefully, you could consider this as two concurrent sphere wall collisions. However, that wall is also moving and providing additional energy to the system. So you have to be careful with it. Okay. And then the other thing to just be careful with considering these sorts of things is make sure that when you are doing it, you are being consistent with your axes. So if you say one direction is positive, make sure that that remains to be the case. So in this, for example, you would say that maybe the UA is positive and the VA is negative. That would mean the UB is negative and the VB was positive. Things like that. But yeah, if you were going to start thinking about modelling those sorts of problems, that would be how you would go about doing it. We're going to do one a step back from that. So we're going to just look at, instead, a successive impact problem that I thought looked quite fun. So it's kind of a long one, so I'm just going to mute myself while I type it out, because otherwise you're just going to get clicking. And in retrospect, I should have done it before. Okay, so figure below represents a top-down view of a horizontal floor with A, B and BC as fixed vertical walls. Can I get away with it there? Yeah. A small ball is projected at wall AB with speed 6 meters per second, and on a path to collide with the wall AB at an angle tan alpha is 4/3. Should note that that one is alpha, that one is beta. Post-collision, the trajectory as tan beta is 1/3 to the wall AB. The coefficient of restitution between the ball and AB is E, and between the ball and BC is 0.5. By modelling the ball as a particle and the walls as smooth, show that E is 0.25, and then find the speed of the ball after colliding with BC, and then suggest two ways in which the model could be more realistic. So immediately the more realistic thing is like, add more physical stuff in. So much of maths is throwing away physical properties that we don't care about. Look at what assumptions have been made, add those back in. So part A of this problem is one collision, part B is another, part C is thinking. We can manage this. So first thing I'm going to do is I'm just going to label all of these as alpha, beta, gamma, and delta. I normally call them alpha, beta, something new, but I really can't be bothered. I'm going to call this speed V and this speed W. just to make my life easier. Okay. So starting from A, we have show that E is a quarter. So equations that we can use, it's impacting in two directions. So first things first, we need to look at the horizontal direction. So remember that was our cos values. So we have our impulse is acting here and our impulse is acting here. So my frame of reference here is going to be, this is parallel to AB. Okay, so that's U cos alpha, so 6 cos alpha is V cos beta. And then this is perpendicular to AB in the vertical. So that's then U sine alpha is E U sine alpha is V sine beta. Okay, the V is by that first value. So we have two equations. What can we do with this? Well, we can work out what cos alpha and sine alpha and cos beta and sine beta are. One of them is going to be nicer than the other. So we have that tan of alpha is 4/3. So going back to my trig functions, tan is opposite over adjacent. Okay, so TOA, so opposite, so 4/3. If I have a right angle triangle where the side lengths are 3 and 4, I know for a fact that that is going to be 5. Okay, it's a Pythagorean it's Pythagorean triple. Similarly then for beta, same thing, this is 1, this is 3, but now this I'm going to actually have to use Pythag for, so it's square root of 1 squared is 1 plus 3 squared is 9, so this is root 10. Okay, so cos of alpha is k adjacent over hypotenuse, so that's 3/5. And sine of alpha is 4/5. Here, cos of beta is adjacent, so that's 3/√10. So 30√10, I think. And then sine beta is 1/√10. So I think for stuff like this, if you were giving it in an exam or you had to work it out, you would just use a calculator, but for the minute, that's what that is. So 6 cos of alpha is 3.6. And 6 sine of alpha is 4.8 E. Okay, so we can just look at these bits of the equation. Okay, and then we can divide them together again. So now we have V sine beta over V cos beta is 4.8 E over 3.6 E. Cancel through the V's, and that gives us that, no E on the second, on that one. Whoops. That gives us that tan beta is 4.8 divided by 3.6, which is something. Some power of 4. But we know that tan beta, we were given it in the question, so that's 1/3. And I'm going to times it by 3.6 over 4.8 is equals to E. And I know that E is 1/4. And I'm hoping that that value gives us 1/4, which it does. Go team. I love a good show question because it means that I don't have to think about it too hard and I can like check my answers, which is always really nice. So part B of this problem was find the speed after collision, so find W. So to do this, first we need to find V, and then we can find W. Okay, so first find v. So remember I labeled the speeds as 6, so u, v, and then w. So we have an equation for v. We could use v cos beta is 3.6 or v sine beta is 4.8e. Let's do v cos beta is 3.6, so that's v, and then I said that cos beta was root 3 over 10, 3 over root 10, 3.6, so that's v is 3.6 root 10 over 3, which is equals to 6 root 10 over 5. I believe. Yes, 6 root 10 over 5. So that's v. Then we know so we were told that the coefficient of restitution here was something. But the ball in BC is 0.5. Okay, so this bit here. So E for E is out over in. Wrong equation. So shifting frame of reference now, we have BC. We'll do it properly. So here we have some value gamma, here we have some value delta, we have W, and we have this is V as 6 root 10 over 5. Some impulse, and we have E is 0.5. Okay, so here doing horizontal, we have V cos gamma is W sine gamma, cos gamma. I really want to put the opposite things there. I don't know why. And then vertical, we have EV sine gamma is W sine delta. Getting there. We want to find delta. We know E and we know V. So we get in the horizontal 6 root 10. Let's just leave it alone. Can we leave it alone? Ooh, I haven't actually finished doing this question. Interesting. We can work out gamma as well. Since we have please recognize that this is a triangle. It's not going to. There we go. Since we got told that the walls AB and BC are at right angles to each other, it was drawn in, which means that B gamma 90 make a right angle triangle. Well, they make a triangle at the very least, but we know 2 are the angles now. So B and gamma. So that gives us that gamma is 90 minus beta, which is 90 minus the arctan of a third, which I think is something disgusting, but good to know. So, trying to find delta here, we can use the coefficient of restitution equation. So we have that E tan gamma is sine delta. So that's 0.5 tan of 90 minus arctan of a third is still tan. Don't know why I keep doing the wrong trig function. Tan of delta. Does this help us? Maybe. Who knows? Is that a nice value? 0.5 times tan of 9 degrees, yeah, 90 minus arctan 1/3. Ah! 3/2 is tan of delta. Well, that's really exciting. Okay. So if we have 3/2 is tan of delta, then I can work out cos of delta and sine of delta. So if that's my delta, then it's 3/2, and this puts this as the square root of 2 squared plus 3 squared, which is the square root of 13. Getting some really gross numbers going on up in here. So, final thing to do is then choose the horizontal equation and then plug everything in. So V cos of gamma is W cos of delta. So V is 6√10. I'm really hoping this turns out to be a really nice number. Times cos of 90 minus inverse tan of 1/3 is equals to W times cos of delta is 2/√13. Blech. Okay, this one is definitely going to be calculated. 6 times square root of 10/5 times cos of 90 minus inverse tan of 1/3. So that side is 6/5. Is W to √13. So that gives us that 6√13/10 is W. And then we should have, throughout all of this, I should have been including my units. That is something that I did not do. So, although coefficient restitution doesn't have any units, so I think I'm mostly okay. Okay, so we have speed of W, speed after the second collision, which, just out of curiosity, we started with 6 meters per second. The initial speed, the second speed then is 6√10/5, which is about 3.7. Okay, and then this one, W is about 2.2. So we're definitely losing speed every time we bounce, which is kind of cool to know. So part C, things that could be made more realistic include friction. And then we got told that it's horizontal floor, so it's moving along a floor. So what would another one be? This is a good question. Oh, yeah, so I suppose the two bits would be friction / roughness on the walls, and then also sort of include roughness on the floor. Right? It's rolling across a floor. It's probably not a smooth floor. So that might be more interesting of a problem. So also considering into the fact that the particle has size and maybe it deforms, all of that stuff. So that is just sort of a brief introduction to elastic collisions. There's obviously so much more stuff going on behind the scenes, but that sort of covers the core concepts of the problems, specifically looking at coefficient restitution and how you resolve impacts at different angles with each other. And then we also covered some example questions.